All right, y'all, we have an objective today. We're going to work on the conservation of angular momentum. So our objective is I can calculate and describe angular momentum using examples. And Mia, I would like your notes to be shared again. So make sure you take those good notes that everyone likes to copy. Um, Jerry, go ahead and mute your mic, and same thing with you, Gabriel. I don't see it muted, but just so we don't get too much. And same thing with you, Ruthie. I'm going to call you Ruthie now. It's not Ruth anymore. I hope you're okay with that. Okay, so there are some resources in Schoology Week 17 that I'm going to need you to look at, mainly because there's not a lot of demonstrations that I can do for angular momentum, digitally. However, I mean, there's people out like Mr. P who does the demonstrations like how I would do them in class. There's just no point in me doing it, and I actually don't have the equipment. So make sure that you are looking at the videos intently. I don't even know if that's a word, but I'm gonna make it up. Is that a word, Kyle? Intently? Attentively? Attentively. Oh, thank you, Gabriel. It is a word. Um, which means with a purpose. So don't think that I don't know that you guys just go on those Schoology videos. No, I didn't say intensely. I said intently, but it's fine. Don't think that I don't know that all year you've been going on those Schoology uh, assignments and clicking through and pretending like you're watching the videos and you're not. You need to watch the videos from Schoology Week 17. Okay, you need to go to Edpuzzle, you need to watch them because there's the demonstrations of these concepts. And if you don't see the demonstrations, then you're not going to understand the the concepts, because we know we have to see and experience physics. Okay, so before we move to the next slide, let's kind of talk about what we already know about just momentum or conservation of momentum. So when we were in the unit momentum, you guys are responding to that survey and telling me that that's a really strong unit for you. So how do we start a conservation of momentum problem? You can either type in your answer, or if you want to unmute yourself, you can tell me. How do we start a conservation of momentum problem? Very good, Gayla Bean. You would, sorry, you would write momentum initial, and we're just talking about linear momentum initial equals linear momentum final. And I'm just going to add, or maybe somebody can tell me, what should we add to Jayla's expression here? There's a really important thing we have to understand about this starting equation. It's not just PI, or momentum initial equals momentum final. It's not just that sum. Thank you. It's the sum of, thank you, Jayla. So the sum of the momentums. And that was important to remember because you have to look at the momentum of both objects. So remember, sometimes we had a collision where one object has a velocity and then the other one doesn't have a velocity. So then, but this was before the collision, and then after the collision, if it was inelastic, they stayed together and moved with a velocity related to their masses. So I hope all that little ideas just came back to your memory really quick. So this is linear, right? And we've understood that in this last rotational motion unit that we're going to do, that all we do is take topics that we've already learned and apply them with the rotational variables, okay? So in the survey, a lot of people are telling me that they're not understanding rotational motion. all we're doing is taking old topics and applying new variables and just changing words like velocity to angular velocity. So then what is the relationship going to be for the conservation of angular momentum, or the starting point? Very good. The sum of L, which we learned is angular momentum, equals the sum of angular momentum final. Okay, and this is where we're going to start these angular momentum ideas. So one of the things I do want to go through is the derivation of how we get there. So to derive it, we're actually going to look at our equation sheet, because we do have the conservation of angular momentum written there somewhere. Let me show you where it is. Okay, so I just pulled up the, what do you say? I just pulled up the advanced placement physics 1 equations, and I want to point some stuff out to you. We have right here, if you can see, let me make a page marker. This equation here, okay, I kind of wanted to do this today because we haven't been able to, be together to look at these. Look at that equation right there. What equation is that we've already talked about? What is this? What equation is that? Good job, Gabriel. Newton's second law of rotational motion. We know it is in this format, right? Sum of the torques equals I alpha, right? That's the same equation here. Okay, so I just wanted to point that out to you. So let's take a look down here. We have, ooh, what's this? What's the next one? What's that? Good job, Gabriel, again. Torque. Okay, so we have torque on there. All right, what's this one? Good job, Jerry. That's angular momentum for just one object, right? Not conservation yet. Oh my goodness. Y'all, okay, story time. You know how I've been talking about how I'm getting a pen, right? I'm like so excited to have a pen. Well, guess what? Neither of them work. I spent $40 on Amazon for nothing. The struggle is real. Okay, like for instance, I'm going to use this one pen. Oh, that's not too bad. No, that's pretty bad. Okay, so that last one's supposed to be angular momentum. And then there's this one right here, this last one that I want to point out. What is that? Change in L equals, good job, Gabriel, keeping your stuff, T times change in time. What is that? Impulse angular momentum. Ew. I guess. Um, what else did we call the impulse equation, though? Didn't we call? Can we call it in? It does sound gross. Impulse angular momentum. That sounds not fun. Um, wasn't this? So I'm looking at the linear version of it, right? Ooh, that's not the right one. Okay. So didn't we use every single time? Didn't we use the linear one when we wanted to calculate change in momentum, or if we wanted to calculate the force on an object? So we can use this guy right here to find our torque on an object if we have change in angular momentum. Okay, so this is the formula that we're kind of working with today, because I can also play with that equation in order to show you that angular momentum is conserved. Okay, so let's go play with this equation really quick. Okay, so the equation was, okay, what was it? Change in L, okay. Equals torque times time. Okay, and I want y'all to sit there for a second and just think about all the things that could be derived within this equation. I mean, think about it. You have a derivation for torque. You have derivations that you can do for L, and so let's see those derivations. Let's go ahead and expand change in L, or change in angular momentum. How do I expand delta L? Thank you, Stephanie. Yeah, Gabriel, you're going where I want you to go, but too far. So expanding change in angular momentum would be L final minus L initial, and then equals torque times delta T. Now, Gabriel, we can use L equals moment of inertia times angular velocity. And we have to be really careful here. So you have to say I angular velocity final minus I angular velocity initial equals torque times delta T. Okay, so there was one big assumption that we had to make in order to state the conservation of angular momentum. Do you guys remember what it was for conservation of linear momentum? What what had to be happening in order for there to be a conservation of linear momentum? It had to be a closed, isolated state. So put that in a closed, isolated system. So in order for there to be no linear momentum, it had to be in a closed, isolated system. Can you put that in another way as well? Because somebody might not know what that means. Okay, so we're trying to define, in order for momentum to be concerned, the objects have to be in a system in which there are no net external forces acting upon them. So we have the same idea. That statement right there that Gabriel just made is for linear momentum. So then how are we going to change Gabriel's statement to apply for angular momentum? So Gabriel said, in order for momentum to be conserved, the objects have to be in a system in which there are no other net external forces acting upon them. So I hope you're thinking in your head right now, what words would I change in that sentence so that it applies to angular? Very good. Jayla wants to say no net external torque, which means for our derivation here that there's no torque. Okay, so torques equals 0. So that means, very important, that this term cancels. So we have moment of inertia times angular velocity final minus moment of inertia angular velocity initial equals 0, which means we just move this initial term over, or we can move the final term over. I think I like it that way. Moment of inertia times angular velocity initial equals moment of inertia angular velocity final. Okay, that means if there's a change in your moment of inertia, which is, remember, your resistance to rotate, or there's a change in your angular velocity, then that can provide different changes as well. So let me show you this in a slide, I guess, or in an animation. I'm just going to let you look at it a few times. So we have this relationship here, and it says the law of conservation of angular momentum. If there is no net external torque on a system, the angular momentum, or L, of the system is constant. Okay, so let me let this thing run a little bit. I'm going to let it run again. I'm not going to talk about it. I want you to kind of talk to yourself in your head. Can y'all see that? I hope you can. If you can't, we're on slide 57. Okay, I'm going to play it one more time, and then I'm going to put up some questions for you to see or for you to think about. Okay, somebody suggested that they're having trouble hearing me. Can y'all hear me? No, I don't think you can because I have to push to talk. How do you push to talk? Hello? Okay, so it was suggested that I move over to doing push to talk, but I know the setting, but I don't know what I have to push in order to talk. So can somebody explain that to me? Okay, let me try it. And I'm changing that setting because y'all are telling me that I'm cutting out, which I appreciate y'all telling me because I don't know. Okay, so I press period. I did. Oh, control period? No. Okay, so I figured it out. Okay, I'm smart. Ooh, yay. Okay, so I hope push to talk ends up working better for us. I'm sorry if I was um, cutting out earlier, but you guys got to tell me because I don't know otherwise. Okay, so I asked the question, why did the moment of inertia decrease? Gabriel said because the radius decreased and the radius and moment of the inertia are directly proportional. So he looked over here. Gabriel, I'd be really careful saying radius and moment of inertia are directly proportional because they're not. They're the radius is squared. So it's not directly proportional. It's like directly proportional to the square of the radius. So then the second idea here is, remember, your momentum is going to be a constant because that's the whole idea of conservation of momentum. So as L is constant, then as the moment of inertia decreases, then angular velocity must increase. This is the famous scenario of a ice skater, and when they have their arms outwards and they bring them in, they go faster. That's a conservation of angular momentum because they're changing their moment of inertia, and when they change their moment of inertia, then that allows angular velocity to either increase or decrease. So that should be an important point to write down, that if you're changing your moment of inertia by changing your radius, then you're going to either increase or decrease your angular velocity. Yeah, so hold on, let me go back. If you're changing your moment of inertia, then your angular velocity has to increase or decrease. So depending on how you're changing your radius, um, in this example, if we're just looking at um, this scenario, I think this is the moment of inertia for a point mass, I think they're using. As they change that radius to be smaller, this is final, that's showing right now. Since that radius of the masses are smaller, then the moment of inertia decreased. So because the moment of inertia decreased, the angular velocity must increase because L has to be the same number. So I'm thinking that maybe this idea is going to get a little bit more solidified if we do a practice problem. So let's go ahead and look at the next slide. So it says the rotating top disk falls onto the rotating bottom disk and sticks to it. Find their final angular velocities, it's supposed to say. So, so let's go ahead. I'm going to give you a minute. Whoa, that's crazy. Okay. Ooh, my slides do not like me right now when I press that button. Okay, it looks okay right now. So there's a disk that's spinning, and then there's another disk that's spinning on the bottom. And I guess we're going to drop the blue disk on the bottom disk, and we're going to find their final angular velocity. Okay, so let's try it. we know that the conservation of angular momentum is Li equals, or the LF. And remember, there's two objects here. That's why we're remembering to put sum. Okay, go ahead. What do you think we should put for Li? Remember, good job, Stephanie. So there's two objects, one for each of the disc. Excellent job. Okay, sorry if you can't see that very well, but it's the moment of inertia for disk 1, or the blue one, times its initial angular velocity, plus moment of inertia for disk 2 times angular velocity initial of the second. Okay, so that's how you express the momentum initially. So what would we do for LF? And y'all explain why Stephanie is writing it like that? She's saying I plus I times W. Good job, Raphael, saying 6 to the disk. So this is a inelastic angular momentum collision. Ugh. Okay, so remember we have to do some algebra here, and we have to solve for angular velocity final. That's what we want to solve for. And if we want to be really good physics students, which we are, we're going to put angular velocity final of 1 and 2 because they're stuck together. Okay, so go ahead, do the algebra while I do it, and plug in your numbers, and let's verify that everyone has a similar answer. You have the right you have the right number, but my answer key says it's negative. Okay, never mind. There's a error in my answer key. I see it. Positive 0.67 radians per second is correct. Okay, radians per second. Okay, I think we need a harder one. What do you guys think? Something harder? Okay, let's try this one. We have a toy car and a turntable are stationary. So initially they are stationary. The car then moves in a circle at a speed of 5 meters per second. Calculate the turntable's final angular velocity. We're given the radius of the car, the radius of the disk. We have the moment of inertia for the disk, and we have the mass of the car. Thank you, Gabriel. I was just going to ask where we should start. So Gabriel's thrown out there that the momentum, the angular momentum initially is 0. So let's go ahead and set that idea up. Okay, what should we write for moment of an angular moment or whatever it is, angular momentum final? What would the relationship be on the other side? Okay, Gabriel is saying moment of inertia of the disk plus moment of the inertia car, which he derived to be point mass m r squared, um, angular velocity final. So basically, Gabriel is thinking that the toy car and turntable represent a inelastic, or like that they're stuck together. So are they stuck together, or is the toy car going to move on the disc? Yes. So in this case, Gabriel, the car is going to move on the disc, so you can't put them together. Yes, Gabriel, we're getting there. Oh my goodness. Okay, now I'm going to derive what Gabriel said already, that we need to find the moment of inertia of the car. Okay, so I hope you're identifying that we have a few things going on here. Um, this is what we're solving for. Okay, we're solving for the turntable's angular final velocity. So I circled that in blue. Uh, we have an issue though because we're almost done with all our variables to solve for. I hope you caught on to the moment of inertia of the car was expanded into mass times radius squared. And then we have this problem. We have angular velocity final of the car, but we were given its um, linear velocity. So how again do we get linear velocity into angular velocity? Thank you, Stephanie. Okay, so I have velocity and I have the radius of where the car's at on the turntable. So I get to use that value. Remember, we want radius from the pivot point. I remember doing these problems. I just had like one of those awful high school flashbacks. You'll understand when you become my age. Um, where I was like, radius of the car or how big the car is? No, location from the axis of rotation. Yeah? Yeah. Can somebody give me a number for the angular velocity of the car, please? And then what about the moment of inertia of the car? Thanks, Raphael. And then here we were given the moment of the inertia of the disk. So we pretty much should be able to solve this. So let me know what you end up getting for your final angular velocity of the turntable. Okay, so we have two people getting negative 2.5 radians per second. So make sure that you can verify that. It's important that we realize that you do the algebra, you move these variables over, and when you move these over, that makes them all negative. Okay, and that's where the negative is coming from. I'm just making sure everyone sees where the variables are coming from. Please take note of that concept about the radius. I really feel like if people aren't watching this video, they're going to continually think that it's like the length of an object, but it's not. It's just the distance away from a pivot point or whatever is the axis of rotation. Okay, are we ready to move on to the next thing? It is 2 o'clock, so I'm kind of thinking of maybe saving what I thought I was going to talk about today for tomorrow. Is that is that Miss A? Oh, well, y'all better go if you have Miss A. Okay, y'all. I'll see you later. I'll be here on office hours. Go ahead and meet with Miss A, and we'll come back together, and I'll send you an email again tomorrow morning. Okay, bye, guys. Take care. We'll finish tomorrow.